So our fundamental idea that we start out with in calculus is the idea of limits. Once again, that talks about the infinitesimal idea of the microness of the mathematics. Okay? Once again, you can relate this back to chemistry. And you look at atoms, and then you go to the micros of protons and neutrons and electrons. That's the microness of chemistry and what occurs in the chemistry world. Well, the microness of mathematics or calculus goes back to the idea of limits. From the idea of limits, we then start deriving other things. But we have to first understand the idea of limits before we can go forward into other things. When, in essence, we've already dealt with some of the ideas that we're going to talk about today. But we're now going to formalize it a little bit more and rename some certain things. What we're going to start talking about today is the idea of derivatives. And when we talk about the idea of derivatives, you're talking about rates. The rates of how things occur. How fast something is changing with respect to another. How fast or slow something is changing with respect to another quantity. Okay, so you're looking at two quantities that are changing here. And how fast or how slow, or at what rate one thing is changing with respect to a second quantity. Well, some ideas of rates. Velocity is a rate. How fast this distance or displacement is changing with respect to time. What is your velocity? The magnitude of velocity in the vector world is the idea of speed. We could talk about acceleration. Acceleration, how fast or how long it takes for your car to go from 0 to 60 miles per hour. That is an acceleration. You push, you flex your calf muscle and you push your pedal down on the right. Okay? And you watch the little digital thing go up, or the speedometer go up, or the digits that are in front of you if you have a digital speedometer, how fast that is going up. That is a rate. How fast you have your velocity is changing. Chemical reactions. The rate of a chemical reaction. You put potassium in water. You put potassium in water and watch the fun. Okay? How fast that chemical reaction is occurring there. But what we have in the math world that we talk about a little bit more is the idea of slopes. Slope is defined to us as delta y over delta x. How fast y is changing with respect to x. And what we have talked about already in this class, we finished up the last chapter, is we found the equation of a tangent line. Where if we found the equation of a tangent line, we need to have a point of tangency, which we were able to calculate. And also, we needed a slope. Well, when we had a slope, we had to determine a slope. Typically, we had 2 points, and with those 2 points, we were able to determine the slope. But if we only have 1 point, a point of tangency, how do we find the slope? Well, what we talked about, how we find this slope, is we took the limit as x approaches a of f of x minus f at a over x minus a. And this allowed us to be able to calculate the slope given only one point. Once again, if we take a look at the idea of a limit, yes, our basis and our idea behind how we found our slope is we took the limit as x got closer to that. So really, in essence, we had 2 points, but we narrowed it down to 1 point, but we had that x plus delta, x minus delta away from our actual point of tangency. Well, what I have here is I have determined the equation of a tangent line of a graph of the function. We're going to go back to what we just talked about. If I have a function here, and let's just worry about 1. And next value -1. And next value -1. What I want you to determine is I want you to determine the equation of the tangent line at x equals -1 of the function x squared plus 7x minus 4. Well, you need to have a point of tangency, and we need to find our slope. So go ahead and find your slope, find your point of find your point of tangency. Pass up. And once again, check your answers with somebody around you. Alex, what was our point of tangency? -1 what? Point of tangency?
Oh, -10.
-10. Okay, finding our slope, Corbin, what do you get for the slope? Value of 5. Okay, so then we go into our equation. We have 5, x minus the -1 equals y minus the -10. And we find our equation. Phoebe, what do you get for your equation? equals y minus 10. What's our total equation? Final solution. Y equals 5x plus the value of 5. And once again, you can have 5x minus y is equal to value of negative 10 also. Or equal to negative 5. This here was what we did up till now. When we found our slope, that can be also classified as the idea of a derivative. So when we dealt with our slope and determined our slope, what we also calculated, yes, we found the slope of the tangent line. At a value of 5. How else we can rename this is a value of the derivative at x equals negative 1. So yes, we can call this the slope of our tangent line at an x value of negative 1, but what we can also rename it as is the value of our derivative at x equals negative 1. Because when I talk about the derivative, we talk about the slope of a tangent line. Well, how do we symbolize the idea of a derivative? When we talk about a derivative, okay, there's a lot of verbiage to say that's the slope of the value of the derivative at x value of negative 1. Okay, so how can we symbolize the idea of a derivative? Well, we can symbolize the idea of a derivative is if I have a function that is f of x or y, and it won't be a function at that point, but it'll be an equation. How we can symbolize this is we put a little prime in there. This little prime symbolizes that we have a derivative. We can also, if we just have a relation y, we can write this as y prime. When you see a prime as a superscript, or a prime to a function or a y, that tells us that we're dealing with a derivative. Well, what we can do with the value of the derivative is we could say, well, this is f prime at negative 1. This will be the symbolization the f prime at negative 1 is the slope at our x value of negative 1. So it's a way of being able to symbolize the idea of a derivative and also a function idea with respect to the function value of a derivative. Other ways you will see the idea of a derivative. dy over dx. dy over dx. Now, where the dy dx comes into the idea, our slope up here is delta y over delta x. That's the algebraic world of our slope. Well, we now go into big boy, big girl mathematics and how we symbolize our delta y over delta x. Well, in the calculus world, when we transfer this from the delta to the calculus infinitesimal, that's where the d's will come in. sort of a parallel to a delta, but in the calculus world, delta is more algebraic. D is going to be more the calculus infinitesimal world. You will also see just d dx. This tells us we're going to take the derivative, and the dx in the bottom tells us with respect to x, and we'll get to that idea eventually. What do we mean by with respect to x? But once again, we're writing it as a rate, sort of like what we have up here. When you find the slope of a tangent line, the slope of a tangent line once again is value of derivative. When you're trying to find the slope of the tangent line or the value of the derivative, they mean the same thing. We can now write this as f prime at a. That's the value of our derivative at a is equal to the limit as x approaches a of f of x minus f at a over x minus a. So when calculating the value of the derivative, you're just finding the slope of the tangent line. So we're referring this right back to the slope of the tangent line equation that we utilized. The value of the derivative, slope of the tangent line, same idea. That's nothing that changes. The problem we run into is what happens if we have to find a bunch of slopes of tangent lines. What we want to be able to develop is a general we want to be able to develop a general derivative rule. A rule for derivatives. So if I have to find 5 slopes of tangent lines, I don't want to have to sit there and go through the slope of the tangent line 5 different times and deal with substitution, canceling, factoring, all that kind of stuff. So I want to find a general derivative and a general derivative rule. So what I want to be able to determine, given f of x, I want to find f prime at x. I want to find a general derivative. So given a function, I want to just be able to find the derivative in terms of x. So if I have my derivative in terms of x, I can find my slope at 0, 1, 2, 3, 4, 5, and so on. I don't have to continue to go through my limits each and every time. Well, for us to find our general derivative, we have 2 methods of madness that we can deal with. We can sort of fall ourselves back into what we just did with our basic idea of slopes of tangent lines. Okay? Or we can use what is called our difference quotient. We have 2 different techniques that we can utilize. What we are used to is f of x minus f of a over x minus a. Well, we want to be able to take this function back into a form of x. So we want to recreate a function and put it back in terms of x. So what we have to do is introduce another variable here. And that variable is going to be the value of t. Rather than approaching the value of a, we're going to approach the value of x, because ultimately Okay, when we were down here, our final solution was, when I found my limit, I substituted that value A back in. I plugged it in, plugged it in. Okay, that was my final idea with respect to a limit. I plugged in my value of A when I was done. Up here, as I approach the value -1, I factor, cancel sub, and then I put in this value of -1. I substituted -1 back in. Well, what I want to be able to do is go back to my general derivative, so I want to be able to substitute x back in. That means I need to have another value at the front because I can't say x is approaching x. So what we have is the limit as t is approaching x of f of t minus f of x over t minus x. So my general derivative can be found by the limit as t is approaching x of f of t minus f of x over t minus x. We could also use the difference quotient, and we'll go through both of these. So looking at the function x squared plus 5, we want to find our general derivative. So we have the limit as t is approaching x of our function value evaluated at t. So we have t squared plus 5 minus our function value f of x, which is just what we have up here, x squared plus 5. And on the bottom, we still just have our t minus x. Distributing, once again, please hold your limits through all this. We have the limit as t is approaching x. We distribute, we have negative x squared minus 5. I'm fine with you writing that up there. 5 and the negative 5, they go bye-bye. So we're left with t squared minus x squared over t minus x. Because the 5s go bye-bye-bye. Be a song in there somewhere. T squared minus x squared, difference of perfect squares. Factors to t minus x, t plus x, over t minus x. T minus x's, they move to Texas. Last step in, for t, I'm approaching x. So I'm going to substitute x in for my t. So we have x plus x, substitute for that x. So we have x plus x or 2x. So our g prime of x is equal to 2x, which now tells me if I want to find the slope of the tangent line at 0, slope of the tangent line at 0 would be 0. Slope of the tangent line at 1 would be 2. Slope of the tangent line at 2 would be 4. Slope of the tangent line at 3 would be 6. Because this general derivative, once again, I can refer this back to a slope and an f prime at a. If we use the difference quotient, we have the limit as h approaches 0 of f of x plus h. So, and for my x, I'm going to put in x plus h. quantity squared, plus 5. So that was my f of x plus h minus my f of x all over h. The first method, if you like factoring, you're going to factor a lot more. The second method, you have to multiply out a little bit more. Where we have limit as h approaches 0 of x squared plus 2xh plus h squared plus 5 minus x squared minus 5 all over the value of h. When using this method, once again, as we dealt with the difference quotient before, all these terms here at the very end will cancel out. Canceling, we can take an h out of all these. And now h is approaching 0. So we have 2x plus 0, which gives us 2x. I'm more of a factoring person. It's interesting, in if you look at your calculus book and go through the calculus book, in the calculus book, they steer towards the difference quotient a little bit more. Okay? And then the alternate is f of x minus f of t minus f of x over t minus x. I find it a little bit easier working with the second one. Because if we take a look at the second one here, we have g of x equals square root of x. I want to find our general derivative. So we have the limit as t is approaching x. F of t minus f of x over t minus x. F of t, square root of t, minus square root of x over t minus x. My t minus x, I could factor that. I can either do a conjugate, multiply top and bottom by a conjugate, or we could factor the bottom down. That's the difference of perfect squares. Which would factor square root of t plus x, or square root of t plus square root of x. Square root of t minus square root of x. These will cancel the 1 and 1. And then we can substitute x in for t. So we have 1 over square root of x plus square root of x, or 1 over 2 square root of x. Now, with this, I will not ask you to rationalize. I will be fine with 1 over 2 square root of x. Now, if you use the other method, limit h approaches 0. We have f of x plus h, so we have square root of x plus h minus square root of x all over h. then you would have to multiply once again by your conjugate. Once again, I like to factor. I don't like to multiply by conjugates as much. But it is doable. Because these will cancel out. So we have x plus h here, minus x, and then on the bottom we have h square root of x plus h plus square root of x. The x's, they go bye-bye. I can cancel out my h's. So we're left with 1 over, as h approaches 0, square root of x plus square root of x, and 1 over 2 square root of x. Once again, more than one way to skin the proverbial cat. Homework's on the back, page 162, 21 to 31. We will be working on general derivatives for a few days here. Just give it a shot, okay? Try to work yourself through some of the problems. Have a good day. Formula sheets out. Make sure you can get the formula sheets out. I'm just trying to give you a little more time here. Okay, identity sheets. You're allowed to have your identity sheets out if you. If you don't have one, if you lost yours, I have them up here and I have some up here if you need them. Your identity sheets. You're allowed to use them on test. Just take them out of your notebook and just have them sitting there.